very much. It's a pleasure to get to, oops. I was saying thank you. It's a pleasure to be here. I'd like to talk about a set of ideas that could be called 𝔸 1-enumerative geometry. So let's say that enumerative geometry counts algebrogeometric objects under certain conditions. Because there are exactly n roots to a polynomial of degree n over an algebraically closed field, in order to get a count that's a number, an invariant number, classically you use an algebraically closed field or C. So satisfying conditions. And in order to have an invariance of number principle, we work over C. So the goal is to record arithmetic information about the fields of definition of those same objects. So record information about the fields of definition. And as in the case of solutions of polynomial equations, there's simply not an invariant number of them. So instead, we're going to cook up various weights associated with the fields of definition and the other data. And instead of an invariance of number principle, we're going to have an invariance of bilinear form principle, or in characteristic not 2, that's the quadratic forms we were just talking about, but will work over a field. We're going to start with an example, and this is joint work with Jesse Cass. So we're going to do an arithmetic count of the lines on a smooth cubic surface. And this is joint with Jesse, who is here. There he is, and there's Jesse Cass, joint with Jesse Leo Cass. Cubic surface is the zero locus of a polynomial of degree 3 and 3 variables. So what is a cubic surface? Is the solutions maybe in C, but then we'll let that field vary. Where F is degree 3. And another principle to get that invariance of number is that it's better to compactify. So we'll put it actually in P3, which has these homogeneous coordinates where not all W, X, Y, Z are 0, and scaling by a non-zero element doesn't change the point. So there's a homogeneous coordinates on projective space, and then we can view the cubic surface as the zeros of a degree 3 homogeneous polynomial in those 4 variables. This is homogeneous degree 3. Okay, so this is smooth if the, say, underlining complex points form a manifold, or if all the partials of F don't simultaneously vanish. And it is a beautiful 19th century result of Salmon and Cayley. That any smooth cubic surface over the complex numbers always has exactly 27 lines. So let X be a smooth cubic surface over C, then X contains exactly 27 lines. Let's do an example. So the Fermat cubic surface is determined by the Fermat cubic, W cubed plus X cubed plus Y cubed plus Z cubed. So what lines do we have on this? So here's one. We could take W equal to minus X and Y equal to minus Z, and then that all cancels out. So here's an ST and P1. P1 is our line. And then, oops, I did that wrong. The line could be S minus S, T minus T. And this is for any ST in P1. And the same trick will work if we chose a different cube root of minus 1. So we could take lambda cubed, well, lambda and omega, such that lambda cubed equals omega cubed is minus 1, and we get more lines. S lambda S T omega T. And if we rearranged the S and T, that will give us even more lines. So in total, this procedure that we've done, we've got, so this produces how many lines? We've got 3 choices for lambda and 3 choices for omega, and then when we pick which two are associated to are paired with each other, that gives us 4 choose 2 over 2, which is 27 lines total on the Fermat cubic surface. This you can actually, in an entirely elementary manner, prove that those are the only lines. There's a reference in the notes, and it's algebra. So let's prove the theorem in general. So here's a modern proof, and we're going to use a characteristic class. And we're going to take this characteristic class, and then we're going to replace it in a bit by an A1 homotopy theory version of the same characteristic class. Okay, we want to count the lines on X. So instead, let's look at all of the lines that there are. Let's let Grassmannian 1, 3 be the Grassmannian parameterizing lines in P3. And this is equivalent by taking the projectivization to parameterizing dimension 2 subspaces. So W, dimension 2. So the C points of the Grassmannian would be parameterizing dimension 2 linear subspaces. So dimension of W is equal to 2. And above this moduli space of all of the lines, we can look at the value of our polynomial. And to do that, let's look at this vector bundle. Let's introduce some vector bundles on this. So we could let S 𝔸1-3 denote be the tautological bundle. And what this bundle does is its fiber over the point corresponding to W is itself W. So that's a definition of this, this tautological bundle. And then we can form the vector space 𝔸3 dual. And this is a vector bundle which over the fiber over the point corresponding to W is all the cubic polynomials on W. So is cubic polynomials on W, i.e. 𝔸3 of the vector bundle is 𝔸3 of the 𝔸3 of W dual. All right, so we have a favorite cubic polynomial, and F determines an element of 𝔸3 of C4 dual. And we can restrict that to any W, so therefore F determines a section of 𝔸3 of S dual, namely actually, by, let's call this section sigma F. And so sigma F of the point corresponding to W will be the restriction of F to W. And then the projectivization of W, so the line corresponding to W is in our cubic surface exactly when the section is 0. So the line, remark, the line P of W corresponding to W is in X if and only if we have a 0, if and only if W is a 0 of the section. So we've changed our problem. So we now want to count the zeros of a section. And there is a tool for doing this. So the Euler class counts the zeros of a section of appropriately oriented vector bundle with a given weight. So let's talk about that. So let's let V to M be a rank R. Looking ahead to when we're not over C, let's pay a little attention to orientations. So over C, multiplication by I kind of gives us, well, it gives us a way to look at orientations. But we're going to want to be more careful about that, so let's work over R for now. So let's let this be rank R vector bundle. And the Euler class, it'll be a cohomology class, and we're going to want to view it as an integer. So let's fix things so we can view that as an integer. on a dimension R real manifold M, and we're going to assume that V comes with an orientation, and we'll talk more about that. So then we can associate to any zero of a section. So choose a section sigma with only isolated zeros. And associated to each section, let's put a particular weight. And this weight can be come up with from the topological degree function. So there is a degree from homotopy classes of maps from the pointed sphere of dimension r-1 to itself to Z that counts the number of preimages of a map. So this is pointed homotopy classes of maps. And we are using it to assign a particular weight to a zero. So right now we're just writing down that function exists. So here comes our weight. So let's let P in M sigma P equals 0. We're going to define, so to define weight degree at P of sigma in Z, here's how. Since the 0 is isolated, we can choose a small ball around P with no other zeros of sigma on it. And then we'll choose local coordinates. So we'll choose local coordinates on M around P. And then there's a small ball around P with no other zeros. And we want to choose a local trivialization of V. And the coordinates and the trivialization allow us to view sigma as a function from R to the R to R to the R. We'll call it sigma. And we can assume that we sent P equal to 0. So 0 will correspond to P, and it's going to 0. And the sigma on some small ball, the ball around 0 of radius 1, has no other zeros in it. So then we can form a function from the SR minus 1. So we have the boundary of the ball of radius 1 going to, again, the boundary of the ball of radius 1 that takes a point x to sigma of x divided by the norm of sigma of x. And we can call this function sigma as well, sigma bar. And then we can define our local index or degree to be the degree of this function. So with the orientations, this looks like a sphere. And we can canonically identify it with a sphere. Now the problem is that if we had chosen a different trivialization that differed by GL of the functions that had, say, a negative determinant at the point P, then this definition here would look poorly defined, because this degree would then change. So what we need to do is we choose a local trivialization of V and local coordinates, and this has to be compatible with an orientation or even a relative orientation. But then we have a well-defined local degree of a section at a 0. And the Euler class, which only depends on the vector bundle and not on the section, can then be computed. So here's the Euler class as the sum over the zeros of the section of the local index. Okay, so we have a tool for counting zeros with a weight, and we were interested in counting zeros of a particular bundle, the sim3 of the dual tautological on the Grassmannian. So it can be shown with some calculus, and there's a reference, that the fact that the cubic surface is smooth, so x was our cubic surface, x smooth, implies that all of these degrees are, well, the zeros of sigma are all simple, so that the degrees are all 1 because we're in the complex case and everything is oriented. So it implies that the degree p sigma is 1, which therefore implies that the number of lines on X is equal to the Euler class of sim3 of the dual tautological. And in particular, this sim3 of the dual tautological had nothing to do with X. So in particular, this is independent of X. And then we saw the Fermat example, or we could compute the Euler class using splitting principle and cohomology of Grassmannians. So we can conclude in a bunch of ways that, in fact, this Euler number is 27. And that's the proof. So what about over R? This is also a 19th century problem, and there's a lot of beautiful things to say about it. An important point to note here is that in the 19th century, Schläfli did a whole bunch of classification of real cubic surfaces, and one of the things that he shows is that X can have 3, 7, 15, or 27 real lines. And in particular, it's not constant. Sigma, pardon? That's right. Sigma is defined by the cubic surface. Yes. And then, hey, the Euler class can be computed with any sigma. So the we're not going to get invariance of number here, but there is an invariant number that can be gotten out of this. And Segre distinguished between different types of lines. So he distinguished between hyperbolic and elliptic real lines. Let's recall the difference between hyperbolic and elliptic elements of the automorphisms of a real line. So L real line, so it's isomorphic to P1R once you chose a variable. So the automorphisms of this real line are isomorphic to PGL2R. We have elliptic and hyperbolic elements of PGL2R.
What part of the proof fails in the real case?
The degree. It's oriented. It's but the degree. There's this fact here. Yeah, good point. So let's pick up some signs. It will still be a simple zero, but then hey, we'll get minus ones. So if we have, we're going to cook up an involution in a second. But actually, well, we can choose any element I in the automorphisms of L. This can be thought of as a matrix, A, B, C, D, or the Mobius transformation, Z goes to AZ plus B over CZ plus D. We can see that there are two fixed points because setting it equal to Z gives you a quadratic equation. So the fixed points of I are the two solutions to a quadratic equation with coefficients in R. So this is it's either well, it could actually be one point, but we're going to have an involution, and so we won't get the one fixed point, the parabolic elements. We'll just have hyperbolic and elliptic elements of PGL2R. So these fixed points either consists of two real points, and then you call the line, the involution. Sorry, then you call the element of the I, so that means that I is hyperbolic, and it's somehow some sort of flow between these two fixed points. And if it's or a complex conjugate pair of points, this is the fixed locus. We say I is elliptic. And maybe here's a drawing. So we're going to associate an involution to a real line, and then if it's hyperbolic, the line will be hyperbolic. If it's elliptic, the line will be elliptic. So we associate an involution I to a real line on a real cubic surface. This involution, for every point on the line, there's going to be a unique other point that has the same tangent space to the cubic surface, and the involution will swap them. And let's see why that's true. If we'll take P on the line, and we want to know what its value is. So we'll look at the tangent space to X at P. That's a plane. And if we intersect with X and look at it, so here's our plane. And then T, P, X. Intersect X is some cubic plane curve. One thing we know about the cubic plane curve is that it has to contain the line, because that's in both of the varieties we're intersecting. So this is the union of the line and something else. And by Bezout's theorem, since the total degree is 3, that something else has to have degree 2. At this point here, you've got the tangent direction on X going by the green and then one going by the red. So the tangent space at this point has to contain the whole plane. And since it's smooth, it has to be equal to this plane. So the tangent space at these points of intersection is TPX. That goes both ways. So these points of intersection, Q intersect L, is the points whose tangent space is TP of X. So this equals points Q such that TQ of X equals TP of X. And it consists of 2 points because the intersection of a degree 2 and a degree 1 curve consists of 2 points. So we'll take P and P prime. And then the involution sets I of P equal to P prime. So that's the definition right there. And then L is elliptic hyperbolic. This is also a definition. When I is. Maybe the most natural way to see that there ought to be distinction between 2 types of lines is actually with spin structures. So a cubic surface is inside 3 space, and so are we. So for a real cubic surface, we've got a real surface inside the room, and then we have a line on this surface. So you can point your finger along the line, and it's smooth, so you have a well-defined tangent plane at each point. So you put your hand along the plane, and then you follow the line, and your hand has to move. And there are 2 things that can happen. You could wind up twisted with the non-trivial element of pi1 of SO3. So you could wind up like that, or you could wind up untwisted, which is sort of a back and forth motion for lines on a cubic surface. And so there are 2 things that can happen. So let's do as an exercise. So here's an example. We'll look at the Fermat cubic surface. There's a better picture in the notes, but so these are the solutions. Actually, let's do it like this. X cubed plus y cubed plus c cubed equals -1. And you can see the 3 real lines from the, we have to choose the -1 root of, third root of -1, and then there were 3 permutations. Those lines all lie in a plane. So there are the 3 lines, and you can view all of the points of the Fermat cubic surface by having a little bubble up out of the paper where there are plus signs like this, and then inside the paper minus signs like that. So what this picture is a drawing of the real points of the Fermat cubic surface. So bubble up and bubble down. Is it clear what's being drawn? So it's like we have to draw a surface in the room, and we have a plane, which is the table, and then in this, the 3 dark lines are in the Fermat cubic surface, and then the part of the cubic surface that's in this triangle here lies above the table, and the parts where you have a minus are below the table. Okay, so we can actually then do this finger trick. We put our finger along this line, and because this is down and this is up, our finger goes like this, and then we go along like this, and then we go along like that. So what do you think? Should I tell you? These are all hyperbolic. So. I should have given you more time for that. That would have been the more fun way to do that. Okay. So alternatively, you get a frame at each point with the line and the tangent space and the normal, and then you're asking if that path in the frame bundle lifts. Although the number of real lines on a cubic surface is not constant, the number of hyperbolic lines minus the number of elliptic lines is constant. And this theorem has kind of an interesting history. It follows from the work of Segre, but there's a claim in print that perhaps he didn't notice it. And then there are some much more modern proofs by Koenig, Telemann, and Finesh and Kharlamov. And these two fit into the framework. This is Kharlamov of the proof that we started with. And then there's a proof using spin structures of Benedetti and Silhol. And there's a proof with Gromov-Witten invariants with Jake Solomon and his student Horev. And we get this nice invariant number that the number of hyperbolic lines minus the number of elliptic lines. And maybe I will give you just another second for fun. So we can tell from our goal was to use the Fermat to figure out Euler classes, or to figure out what this invariant number had to be. We're counting over real lines. There were 3 of them. We said they were all hyperbolic, so we got 3. All right. It is a general principle that if you have a result that is true over the complex numbers and over the real numbers, then maybe it is a result in 𝔸1 homotopy theory that has realizations that give the previous results. 𝔸1 homotopy theory due to Morel and Vavadsky. Allows us to do with schemes many of the things that we can do with topological spaces. And smooth schemes then behave like manifolds. In some sense, they're little small balls around points. And one of the beautiful results in 𝔸1 homotopy theory is a degree homomorphism of Morel. So we're going to have spheres that are the quotient of Pn over Pn minus 1. If you build projective space from smaller projective spaces, you add a single cell. So this is a sphere if you took this over R or over C, and it's a sphere in 𝔸1 homotopy theory. And there is a degree map from 𝔸1 homotopy classes of maps from this sphere to itself to not the integers this time, but a group of bilinear forms or quadratic forms when k is not 2. So this is Morel's degree homomorphism. It's an isomorphism when n is at least 2. GW of k, this is, let's say, on smooth schemes over k with k a field. So GW of k is the Grothendieck-Witt group. Its elements are formal differences of bilinear forms. So this is the group completion allowing for formal differences of isomorphism classes of bilinear forms beta v cross v to k, and this is a finite dimensional k vector space. So we can, if we had two bilinear forms, we can make a bilinear form on the direct sum of the associated vector spaces, and by declaring elements from the two different ones to be orthogonal. So that's the summing operation that then we allow formal minuses of, and then we'll inherit ring structure from the tensor product. So just, and we've got direct sum and tensor product of forms. So the claim is that this group is both complicated enough to be interesting and concrete enough to give interesting computations. So it has a presentation. We're going to talk more about this group tomorrow, but bilinear forms over fields can all be diagonalized in characteristic 2 stably, so you have to add something before diagonalizing. But if you can diagonalize, that means you've got generators that are the one-dimensional forms. And I forgot, isomorphs of non-degenerate symmetric. Excuse me. So we need non-degenerate, symmetric, bilinear forms. So this corresponds to the isomorphism class of form on one-dimensional vector space K that sends xy to axy. If we change the basis of K by multiplying by B, we get that AB squared is equal to A. So the generators are really in K star over K star squared. And there's one other relation, which says that A plus B is equal to A plus B plus AB, A plus B. So it has a simple presentation, and there are also books written about computations for local fields, for global fields, for finite fields, for function fields. There's a lot known for specific examples, and for right now, let's do some examples that show this principle, that you could get an A1 homotopy theory result and then look at it over C and over R and get results that you wanted to generalize. So the Grothendieck-Witt group of an algebraically closed field, the generators are in bijection with K star over K star squared, and everything is a square, so there's only one generator. So this is Z, and an isomorphism is given by the rank homomorphism, which takes beta to the dimension of V. And the Grothendieck-Witt group of R, we saw in Jacob's talk that all forms can be diagonalized with ones and minus ones, and that we have this signature, which is the number of ones on the diagonal minus the number of minus ones, and that goes to Z. And then we still have our rank. And there's a parity issue, but this gives an isomorphism with Z cross Z to the Grothendieck-Witt group of R. The last example that we'll use in the talk today is we can take the Grothendieck-Witt group of a finite field, FQ, And if we make a matrix out of taking the value of beta on pairs of a basis element and then take the determinant, we get an invariant called the discriminant. And then we still have the rank. And the determinant of a matrix, a non-degenerate bilinear form, is in F star. And if we change the basis, we multiply by A transpose on one side, A on the other, and that is well defined up to squares. And we get a map like that, which is also an isomorphism. So we have an extra Z mod 2 hanging around in the growth and degrade group of a finite field. Okay. There is an Euler class in this context. So if we take, we're going to talk about this more, but there is an Euler class. E for a relatively oriented vector bundle, and it'll be a sum of a local degree of a section. And so let's believe that the proof that we started with will produce another result in this context. And what result does it produce? Let's let K field of characteristic not 2, and X smooth cubic surface over K, a line L and X, it'll be a closed point of the Grassmannian, so we can think of it as points of the form AB, or A, B, C, D, S plus A prime, B prime, C prime, D prime, T, with S and T in P1 over some other extension field. So the line will be defined over a field K of L, which is K adjoin these coefficients, or equivalently, if you view a line as the zero locus of two linear equations, you'd get some field of definition. So line is a closed point of the Grassmannian, and so it really determines a closed subscheme isomorphic to P1 K of L inside X over K of L inside P3 over K of L. So the lines are like we solved for in the Fermat. We could take these cube roots of -1 and let's remember that they're there. So given a line L, the same recipe, so given a line L on X, we obtain an involution I in aught L, which after a choice of coordinates is PGL2 of K of L. So now the fixed points of I are, it's either 2 K of L points or a conjugate pair of points in some quadratic extension. So we can adjoin a square root of D for a well-defined D in K of L star over K of L star squared. And these are the points where that tangent space pauses. So as we travel along the line with our tangent space, we have 2 points where we temporarily stop, and they're defined over adjoining a square root of d. So let's define the type of L to be bracket d inside. I know from the last talk that that's probably not my time. No? Yes? Oh. Okay. We're almost done. In growth and Witt group of K of L, there's some equivalent. This is equivalent to, we could let D equal AB minus CD if we choose a coordinate, and we have this. We could also have a type of L is -1 times the degree of the involution I. The type of L is picking up something about how the tangent space is moving along the line. And the theorem same hypotheses. Is that if you take the sum over the lines L of X of a map which picks up the field of definition, I'll tell you what it is in a second, of this trace of K of L over K of the type of L, you get one fixed quadratic form. So this trace map or transfer map is a map from the growth and Witt group of K of L to the growth and Witt group of K. It turns out these extensions are always separable, and so in this case it takes the form beta to a form where we now view V as a vector space over K instead of K of L, and we do beta. But we want to be a quadratic form over K, so we compose with the trace from Galois theory that sums the Galois conjugates. So we have a well-defined map in the other direction, not restricting quadratic forms, but this is because the growth and Witt group is a stable homotopy group of spheres. We get backwards maps. Okay, so this left-hand side is picking up aspects of the field of definition of the lines on your cubic surface and of their tangent space, how the tangent space moves along the line. And this is one fixed quadratic form. And the quadratic form it is 15, 1 plus 12 minus 1. And let's see what happens over C. So we'll take K equals C, and we know that that the information is contained in the rank. So the rank of this form is 15 plus 12 is 27. And the type, it was bracket an element in K star over K star squared. There's just one of those, that's 1. So what we get is that the number of lines equals 27. And when K is equal to R, we can apply the signature. We could have a line that was defined over C, in which case the type is 1, and we get the trace form of C over R, but that is 1 plus minus 1, and that doesn't contribute anything. So what we then get is the lines over R, and it was set up so that the type 1 lines are the number of hyperbolic lines minus number of elliptic lines. And that's the signature of this form. That's 15 minus 12, which is our 3. But let's do something new. So let's take K equals FQ. We can have lines defined over any FQ to the D, and then the type can be the square class in FQ to the D star, or the non-square class. Since there are only two of those, we might as well call them elliptic and hyperbolic. So if you're the square class, call yourself hyperbolic, because that was like 1. So what we get from computing trace forms is that we get that the number of elliptic lines with field of definition with K of L, an odd degree extension, plus the number of hyperbolic lines with an even degree field extension, has to be the discriminant of this form, which is 1 to the 15 times minus 1 to the 12, which is 1, which is the, in Z mod 2, 1 is 0, so it is even. All right, so I'll stop there. Thank you.
Is there anything known about Grothendieck-Witt group over p-adix?
It's got, so it's 2 copies of Witt group over FP. That's for the Witt group. So as a group, it's the Witt group is when you divide out by the hyperbolic element 1 plus minus 1. And then the Witt group of the p-adix is the direct sum of 2 copies of the Witt group of FP, and then the Grothendieck-Witt group is just an extension by you cross over the Z mod 2 rank homomorphism with Z.
Thank you.
Oh, sorry.
I'm curious. Oh, I have the wrong way. I have a loud voice. It doesn't matter that much. I mean, there's lots of enumerative results in algebraic geometry. I mean, is it easy to see which ones are amenable to this kind of thinking that can be, or is this really true for like anything? Is any number that Joe Harris would tell you amenable to this kind of thinking, or is it a subset of those problems?
Yeah, I'm curious about that question. Well, one thing that can happen is that you might not get relatively random line bundle like you call it. So there.
Now, yeah.
So if you okay. So if you take the intersection of 2 quadrics in P4, for example, a nice Del Pezzo surface, and you want to recover those 16 complex lines, and there are cool things to say about the real lines, that is unfortunately not relatively orientable, because P4 is canonical class is O minus 5, which is not a square, and we're taking a complete intersection of 2 things, so that's a section of 2 copies of sim2 of the dual tautological, and so one of them's even, one of them's odd, and you don't directly get something like this. That said, in Matthias Wentz's paper on oriented Schubert calculus, that case is in there in a way that I would like to understand better. So, I mean, we'll see. So if you mean about the involution, no. If you mean about that there's some sort of local index, yes, but it's not clear what the, I don't think you get any new information in characteristic 2 about cubic surfaces from the Euler class computation, and I am not sure what a good substitute for that involution is.
Okay, maybe let's thank Kirsten again and take a 15-minute break.